All right, we got the connection going here. So this is week 4, and in week 4 we just have the test to do this week. There's nothing else. So you don't have to worry about doing a quiz. You don't have to worry about doing a science and digital literacy assignment. However, if you want to catch up on the last 3, that's fine. You can still get them for full credit. So this week, test 1 is over chapters 1, 2, and 3. Okay. So one thing you'll notice is that I kind of removed all the timings on the test. So that means you can open it up and take your time on it. So one of the ideas behind this is, yeah, it's worth 100 points, but it's not as quite of, I don't know how to say it. Yeah, you can take your time on it, look things up. It's open book, open note. I don't really care. I want you to learn. That's the main part here, is I want you to learn. Now, at this point, this is a good time where anybody can ask me a question about the material. And before I start answering your questions, though, I just want to talk about the essay question really quickly. Okay, so one of the things that's different is I wanted you guys to write a little bit for this test, not just try to figure out multiple choice questions. One of the things with being online is, well, you're just not going to memorize as much for this test. But what I want you to do is have an understanding for it. So this 20-point essay question, it's a big one, right? So spend your time on it, get it done right. It should be a minimum of about 500 words. That's just a kind of a guideline. I'm not going to give you 0 if you don't have 500 words, but that's just kind of a guideline. And this is an opportunity for you to kind of, think about things that you learned and explore something that you thought was either very interesting or was important. And so that's your first thing. So when you write your essay, I want 4 paragraphs. The first one is going to be the shortest one, of course. But what is the most important or interesting thing to you? It can be anything. And I know I've graded a few tests, and you guys love the astronomy lesson so far. And I think that's awesome that in a biology class that we're making that connection to life on the planet to astronomy. I love that. That's awesome. But it could be anything. I mean, it could be the scientific method. It could be the limitations of science. Anything. It doesn't matter. It's just what you like or you thought was important. So the next thing is I want you to explain, why did you find it interesting? Why did you find it important? This is 5 points. So explain to me. Pretend that you're trying to explain to me, your brother, sister, boyfriend, girlfriend, husband, wife, kids, parents. Why is it interesting? Why is it important? That should be a paragraph. Tell me why. Don't just say, I like the Big Bang because it's kind of cool and we all came from stardust. Well, that's a good answer. It's just kind of incomplete. So details and examples matter. The next one, fully explain your topic. If you talk about, you thought that the limitations of science or the scientific method was really important, explain to me the scientific method. Yes, you'll include the nuances. The scientific method is a series of steps that begins with making observations and asking questions, followed up by forming a hypothesis, going out and testing our hypothesis, and repeat. You would explain that. And you might explain also that with the scientific method, that it's not a rigid set of steps, but it's this guide of how we do science. If you were to talk about the Big Bang, I know it's kind of weird in a biology class, but a lot of you guys like that. And we are connected to the Big Bang. It did matter for biology. You might explain, when did it occur? How do we know it occurred? What's the evidence for it? What was created there in the Big Bang? What wasn't created there in the Big Bang? These are all very important points. Okay. And then lastly, your 4th paragraph here, look up additional information that's not in the reading. Now, I know a lot of professors, a lot of teachers are really down on the Wikipedia. I'm not. It's the greatest thing that's ever been created on the web. No, I'm serious. And some of you guys are laughing and you're shattered. That you've always learned, don't ever trust the Wikipedia. You know what? Wikipedia is great. And tell your teachers if it's wrong or bad, tell them to go fix it. But look up additional information. You can use anything. Just make sure they're reputable. But look up that additional information that's not in the reading to add to it. That should be a paragraph. So if you talk about the Big Bang, tell me something that's not in the book. If you talk about science, tell me something that's not in the book. Okay, so that's a 20-point essay question. Like I said, spend some time on it. You can write it, literally write it in a Word file, and then just plop it right into your essay here. Okay, so now I'm getting some questions. Are all the resources for chapter 3 online? I had trouble with questions on the quiz. Didn't remember covering certain things like making a molecule hydrophilic. Okay. Granted, in the last year, one of the things I've done with this class has cut out some of the details and explanations in the chemistry section. So for instance, in this class and on this test and on any quiz, you're not going to learn about functional groups, methyl groups, hydroxyl groups, carboxyl groups. I had a hard time taking that out. I think it's important, but I think we can get by without it. But all the resources for chapter 3 should be online, especially for the quiz. Like making a molecule more hydrophilic. That's a good point. I actually didn't cover, and I'm removing everything about adding hydroxyl groups to make something more hydrophilic. But you do need to know what hydrophilic means. Hydro means water, philic means loving. Hydrophilic is water loving. Any molecule that's water loving will dissolve in water. Sugars, alcohols, they dissolve in water because they are hydrophilic, and they can form hydrogen bonds with water, and that's important. So yeah, I'll double check the questions, because if I have something in there about making a molecule more hydrophilic, don't worry about that. It's not on the test, and neither are the functional groups. Okay, emergent properties. So Philip, add on to that, emergent properties. What do you need to know about emergent properties? What do you not know? What do you want me to explain about emergent properties? Emergent properties are on the test because, two things about it. Life is the result of emergent properties. And emergent properties are these new properties that emerge with each level of complexity. So a great example is you take hydrogen gas, hydrogen, which is a gas, oxygen, which is a gas, put them together, you make water, it's a liquid. Liquid water is an emergent property by putting two gases together. Sodium chloride, that's table salt, a food additive. Sodium is a metal that catches on fire in water. I know, that's really weird, isn't it? Chlorine is a gas that will kill you. Put them together, you have table salt. That's an emergent property. So as we go up in complexity, new properties arise, and life is the result of emergent properties. And one other thing about emergent properties, you can't always predict them. That means I can know everything about protons, neutrons, and electrons that make up us. That does not mean that I can make predictions about you. That's an emergent property, because we can't always predict those emergent properties. I believe that one's on the test. Okay, I have a question regarding acid, bases, and buffers. Mainly buffers. Can you explain how buffers work? Oh, that's a fantastic question. So acids and bases, what they do is they change the pH of water. And pH is a measure, it's called potential of hydrogens, hence pH. And you can be acidic or you can be alkaline. As you go down in pH, going from 7 to 6 to 5, 4, 3, 2, 1, you're getting more and more acidic as you get more and more hydrogen ions. Now, for all you chemistry buffs, I know it's hydronium, but hydrogen ions. And hydrogen ions are reactive, which means they affect chemical reactions. If you become a base, you have 7, which is neutral. The hydrogen ions equal the hydroxide ions. That's water splitting apart. As you go into becoming a base, you have less and less hydrogen ions, but you have more and more hydroxide ions. So you go 7, so 8, 9, 10, 11, 12, 13, 14. That becomes more and more basic. Hydroxide ions, like hydrogen ions, are very reactive. They affect chemical reactions. So your body has all of these chemical reactions that take place. And those chemical reactions are made possible by proteins. And those proteins operate in a very narrow range of pH. So what happens is we don't want the pH of our body, of certain parts of our body, to change, including our blood. So our blood only works between a pH of like, I always forget. 7.3 to 7.4, 7.35, 7.45. It's a very, very narrow range, because if it becomes too acidic, you get into acidosis. If it becomes too alkaline, pH goes up, it becomes alkalosis. So what we have is a buffer. And what that buffer does is it prevents the pH of your blood or any other substance from changing wildly. Okay, and here's how a buffer works. A buffer can act as an acid. It can act as a base. It depends on the pH of a solution. So let's think about your blood. You start exercising. You're using more oxygen. You're producing more carbon dioxide. Carbon dioxide dissolves into your blood. It actually forms carbonic acid. Your blood levels, your pH of your blood goes down. It becomes more acidic as you exercise. But if your blood becomes too acidic, then it can't carry oxygen and carbon dioxide very well anymore. So what it does is it has a buffer. As your pH begins to drop inside your blood, a buffer acts as a base, okay? And it acts as a base by taking up hydrogen ions. So it reduces the concentration of hydrogen ions, okay? So a buffer can act as an acid or a base. So if your pH of your blood begins to go down, a buffer will act as a base by removing hydrogen ions. Now, let's say you're resting, and let's say you eat some really alkaline, I don't know, I'm not going to use that example, but let's say your blood pH begins to go up, becomes more and more alkaline. Well, that's bad too. In this case, your buffer will act as an acid, and it acts as an acid by releasing hydrogen ions and causing the pH to go back down. So that's why buffers are very, very important, because they help maintain the same pH by acting as an acid or a base. And I hope that answers that question. Okay. How would you like for us to vote our sources? You mean cite our sources for additional information? People get really worked up about citations. Just tell me where you got it from. Just give me the link to the website that you went to, or tell me the name of the book or the name of the article. I don't really care if you use MLA citations or not. It doesn't matter to me. Web links are great. Because sometimes you guys are going to go find something that's really cool. You're probably going to teach me something, which is awesome. And I want to go read the articles that you're looking at, because I'm interested in this stuff too. So yeah, I'm not really worried about the citation. Just let me know where you got it from. Put me a link on there where I can go find it. Okay. How do you know when bonds sharing an electron and if they are sharing it evenly or not? Ooh, Savannah, that's a really good question. Okay. Covalent bonds share electrons. Co means with. Valence has to do with valence electrons. So imagine this, you've got an atom, and in the center of that atom is a nucleus. And outside that nucleus are the electrons. And electrons like to exist in pairs. They like to exist in pairs, and you like to have 8 of them, which is kind of cool. So to complete their valence shell with 8 electrons, they share electrons with other elements. Okay, so for our purposes, if you ever see the elements carbon, nitrogen, hydrogen, oxygen, those are the 4 most abundant elements, and they share electrons with each other. Okay. Now, other elements will also share electrons too. Sulfur shares electrons. But carbon, nitrogen, hydrogen, oxygen, they share electrons. Now, how do you know if they're sharing them equally or not? That has to do with the property of an element called electronegativity. Electronegativity is a function of how well it attracts electrons. So electrons are negatively charged. Protons are positively charged. So if we look at carbon, nitrogen, and oxygen, carbon has 6 protons, nitrogen has 7 protons, oxygen has 8 protons. As you increase in protons from 6, 7 to 8, that increases the pull on the electrons. All right. So oxygen is the second most electronegative element in the universe. That means anytime oxygen forms a covalent bond with any other element, with the exception of light itself, oxygen, it is not sharing them equally. It forms a polar covalent bond. So anytime you ever see oxygen bonded to hydrogen, carbon, or nitrogen, they are not sharing those electrons equally. Okay? Same with nitrogen. Nitrogen has 7 protons, carbon has 6. Nitrogen will form a polar covalent bond with carbon and with hydrogen. Okay, now they're sharing electrons equally. Oxygen bonded to oxygen. That forms molecular oxygen. Nitrogen to nitrogen, that's the nitrogen in the air we breathe. Carbon to carbon, those are all non-polar covalent bonds. Now, carbon has 6 protons, hydrogen only has 1. But hydrogen only has 1 electron shell. Carbon has 2. So the electrons, instead of being very close to the nucleus, are out here, which means that the nucleus of a carbon atom has less of a pull on those valence electrons. So that means carbon covalently bonded to hydrogen shares electrons about equally. It's not perfectly equally, but we would still consider that to be a non-polar covalent bond. Okay, so carbon to carbon, non-polar, and those form hydrocarbons, which are also hydrophobic. And hydrophobic substances can't dissolve in water because they can't form hydrogen bonds. Okay. Just the basics about emergent properties. All right, I think I just did that earlier. You know, an emergent property is a new property that emerges with increasing complexity. And as I explained, you know, you take oxygen and hydrogen, 2 gases, put them together to form water. Water is a liquid. Sodium and chlorine, poisonous gas. Sodium's that metal that catches on fire in water, which to me is just fascinating. And you have table salt, which is an emergent property. Life emerges at the level of a cell, and life, you know, are these little islands of low entropy that maintain the taking energy to create order, maintain homeostasis. And that's an emergent property because they use all these metabolic reactions inside the cell to do that. So life is an emergent property of a very complex system of all these molecules interacting together. Do we need to know how to classify life within 3 domains? You know, that's it's a really easy thing. Think of all plants, animals, fungus. Everything that you see around you would be a eukaryote. And then bacteria and archaeans form the other 2 domains. And I'm not going to talk too much about them until we get to chapter 5, where we talk about the cells. And other than that, that's all you need to know about that. That we do have this classification system to classify life. And the most inclusive one would be animal kingdom, because that includes all animals, so it's including everything. And the least inclusive or most exclusive would be a species, because a species would only include like humans or house sparrows or dogs or wolves or whales. Well, no, whale would be an actually family. Okay. Do we have any other questions? You guys, this is the time to go ahead and hit me up. I don't care if you have your test open and ask me questions. Just don't shoot me a question about about what the answer is for a test question. That's not cool. But you can ask me about any of the questions on the test if you have it up and want to take a look at it. I'll give you guys just a minute here to do that. Then if not, I'm going to sign off and make this available on Learn for you guys. Okay. Sydney, could you talk a bit about the universe expanding, just out of curiosity? More specifically, could you talk about how some galaxies are moving faster, they're further away, and why? Man, I love talking about this stuff. I know it gets out of the realm of biology a little bit, but hey, you know, biology is connected to the universe. So in the 19 teens and 20s, it was thought that our universe was the Milky Way galaxy. That was it. And then we built all these really big telescopes, and they started looking, and they discovered that all these fuzzy things that they thought were nebulae were actually individual galaxies. And Edwin Hubble started analyzing the light coming from them, and so did this other Italian astronomer called Lemaitre, or French, right? Lemaitre. Can't pronounce his name very well. But they realized that the light coming from them are redshifted, and that the further away a galaxy is, the more redshifted the light was, meaning the faster it was moving away from us. Remember, light travels in waves, right? If you're moving away, the wavelength is elongated, so it looks reddish. If something's moving away from you, the wavelength is shortened, it looks bluish. Okay, so everywhere he looked in the night sky, these galaxies were redshifted. They were all moving away. And what he noticed was the further away the galaxy was, the faster it's moving away from you. And My daughter's got tons of balloons and I don't have one around me right now. But okay, imagine this. Take a balloon. This is a thought experiment. This is what Einstein used to do. Take a balloon and imagine putting dots on the balloon. All right, each dot represents a galaxy. Now you go and you blow the balloon up, right? And as the balloon expands, the distance between the galaxies expands as well. That's the universe. It's expanding. And the fabric of the universe is actually expanding too. So just like the balloons that dots are, the balloon itself represents the fabric of the universe. And as you add air to it, those dots move away from each other. A dot that's close to you moves away faster than a dot on the other side of the balloon, and one that's closer to you moves away less slowly. That's why we see galaxies moving away faster from us the further away in space they are, because there's more space away between us that's expanding more and more. Do the balloon experiment. I mean, I can't believe it. I got a whole package of balloons in there. It's a great experiment to show like the expanding universe. The reason why the universe is expanding is because based on every bit of evidence we have, the universe began. I got a little piece of dirt here. Is it something like this big? Well, actually infinitely small. And then there was a quantum singularity event. I don't know. And it just blew up. And there was this time of inflation where the universe just went from like infinitesimally small to most of the size it is today in a very incredibly short amount of time. And why the universe began with a Big Bang, we're not entirely certain. That's what scientists are trying to figure out right now. But when it comes to understanding how the universe works and quantum physics and these things, one of the hardest things that we have to let go of is we always think something has to come from something. You can't get nothing from something. You can't get something from nothing. And that's not entirely true at the quantum level. And we've shown that over and over and over, that you can actually get something from nothing. Virtual particles pop in and out of existence all the time. It's just crazy. Okay, I got another question. How do you know if something is a closed or open system? Okay, here's a great example. This is a really good thermodynamics question that I like to think about with life. You and I are open systems. We constantly have a supply of energy flowing through us. Sounds like the force, right? We got the force flowing through us. But we do. The foods we eat contain energy. And right now, you're radiating energy from a photon. So that means you're a luminous being of light, but you're radiating energy out of you, and that energy came from the food you ate. So we are an open system. Nutrients and energy flow through us. A closed system, there are hardly any closed systems. The universe itself is a closed system. Imagine taking your room and just walling it off, and nothing can get in or out of that closed system. That would be a closed system. And closed systems always go to high entropy, which is a measure of disorder. So if I were to wall this room off, I would burn through all my energy, then I'd be very morbid. I would decay into a bunch of dust and oxygen and carbon dioxide, and then that would be it, and that would be the end. And then if this room were totally sealed off, it would stay about 80 degrees in here till the end of time, and things would just slowly decay to equilibrium. Oof, rough. You don't ever want to be in a closed system, except our universe. Okay, is it true that some galaxies are moving faster than light, and that doesn't break any laws? Theories. Let me see if I can explain this here. No particle of matter can go faster than the speed of light. That's Einstein's equation, E equals mc squared. Energy is equivalent to mass times the velocity, the speed of light squared. If you don't know the speed of light, it's super fast. It's like 186,282 miles per second. You can go around there 7.5 times in 1 second. So the reason why Einstein's theory is so awesome is because you can't go fast. You can't take a matter to go faster than the speed of light. The reason why is because you know this from everyday experience. The faster you go, the more energy it takes. So you can walk very easily a mile. Can you run a mile? It takes more energy. Can you sprint a mile? Oh God, there's no way I could sprint a mile. It would crush me. I could easily walk a mile. Because the reason why I can't run a mile is because it takes more energy to go faster. So as you approach the speed of light, it requires more and more and more energy to push matter toward the speed of light. And at that speed of light, it basically takes an infinite amount of energy to go faster, right? So you can't so there's not enough energy in the universe to push objects of matter past the speed of light. Now, I'm going to come back to your question here, but our connection to life is that kind of makes, as you know, life, it makes it harder for us to go fast all the time because it uses more energy. Now, is it true that some galaxies are moving away from us faster at the speed of light? They are approaching it, but they're not breaking any laws. And the reason why is, imagine my balloon expanding experiment. Relative to them, they are not moving faster than the speed of light. It's just that the fabric of the universe is expanding. And as you go to the edge of the universe, which is nearly 40, well, there's no edge. It's like asking the edge of the planet on a two-dimensional being. There's no edge of the universe. But as you get further and further and further away, the fabric of the universe is expanding fast, more and more and more between us. And relative to us, it's the speed might be approaching or even faster than the speed of light. And eventually, the universe will become so large that we won't be able to see those distant galaxies anymore, because the light won't be able to catch up with the rate of the expansion of the universe. But that's not breaking any rules of physics, because it's just the fabric of the universe is expanding, not matter. Okay. Can I explain the basics of isotopes? Okay. So isotopes are, you have an element. Let's take an element like carbon. Oh, I'm getting photobombed by my dog. Say hi, Dax. Hi, Dax. Okay, so you got an element like carbon. And carbon, an element is defined like carbon by the number of protons in the nucleus. So carbon will always have 6 protons. Nitrogen always has 7 protons. Oxygen always has 8. Now, an isotope is, we have the atomic mass. So also inside the nucleus, you've got a proton and a neutron. Going back to carbon. In carbon, you always have 6 protons. You change the protons, you get a new element. But you can have 6 carbons. Thanks, sweetie. You can have 6 carbons. You can have 6 neutrons, 7 neutrons, 8 neutrons. Okay? That gives you carbon 12. 6 protons, 6 neutrons equals 12. That's carbon 12. You can have carbon 13, which would be 6 protons, 7 neutrons, and of course carbon 14, which we're familiar with, which has 8 neutrons in its nucleus. And an isotope differs in its mass. So carbon 14 is heavier than carbon 12, but the other chemical properties of carbon remain the same. Carbon 14 can form 4 covalent bonds and form any amount of organic molecules, just like carbon 12, except you wouldn't want to use carbon 14 because it's radioactive. It will decay into nitrogen 15. So some isotopes are stable, like carbon 12, carbon 13. They can last 10 to the 25 years, a billion, 100 million, billion years. That's a long time. They're basically eternal. But other elements or other isotopes are radioactive. And what that means is they have an unfavorable ratio of neutrons to protons. So they decay to daughter elements through what is called a half-life. And they decay into the other stable elements. So carbon 14 decays into nitrogen 15. One of those protons, not nitrogen 15, nitrogen 14. So a neutron emits an electron, becomes a proton. So you go from 6 to 7, you become nitrogen, and that's stable. So that's how isotopes work. And a half-life is basically, if I have a pound of carbon 14 in 5,200 years, I would have half a pound of carbon 14. So a half-life is a time that takes half of that substance, that radioisotope, to decay into its daughter cells. Okay, how is the fabric of the universe defined then? Oh man. The Higgs field. There you go. It's just the space between us. It's the universe. I have to think about that one. Sydney, you got me. I will think about that one and how I can answer that. Okay, Alexis, at our most fundamental level, what are we made of? Okay, that's a good question, because a lot of times we get confused about this at our most fundamental level. In this class, the basic building blocks of matter are protons, neutrons, and electrons. Those 3 subatomic particles make up the elements. So carbon is made up of those 3 subatomic particles. So whenever I'm asking about fundamental building blocks, I'm talking about protons, neutrons, and electrons. They make up elements. Elements make up they make up molecules. Molecules make up cells. So I hope that clarifies that question. A lot of people get confused between elements and the subatomic particles. And my connection going back to the universe is protons, neutrons, and electrons, and especially protons and electrons, they were made during the Big Bang. They're 13.7 billion years old. And so are many of the neutrons inside of us as well. But neutrons are also made inside of stars through nuclear fusion. So the neutrons inside of you could be anywhere from 13.7 billion years old to as young as 5 billion years old. Young as 5 billion. That's pretty wild, isn't it? Okay. Any other questions popping up here? We're all good? Okay. Well, good luck with the test. I will be around on email until tomorrow about noon. And then afternoon, I have to go do some, I got to have downtime from the screen. Okay. Here we go. We got a couple more. I don't remember seeing uniformitarianism before. Okay, it's in the book. It's in chapter 1. And in fact, I updated chapter 1 just to make sure it was in there. And I can throw in a little bit more on the PowerPoint. Think about this. Uniformitarianism is an incredibly important scientific principle. Uniform. Uniform means the same. If somebody's wearing a uniform, they're all wearing the same thing. That's what uniform means, all the same. Uniformitarianism. This is a scientific principle, and it says that the laws of nature, like the laws of physics that operate today, the way nature works, the way our universe works today, works the same everywhere in the universe. So if I study our sun and understand how it's working, then I can look across the universe at another star, which would be almost impossible, but if I were to see another star, I would know it would work the same way, because the laws of nature are the same everywhere in the universe. They are uniform. Not only are they the same everywhere in the universe, they are the same in the past. So the point is, the way that the world operates today is the same they would operate in the past and in the future. That allows us to make predictions about what's going to happen in the future as well. So basically, the uniformitarianism says that the way nature works today operates the same everywhere in the universe, works in the same in the past and in the present. That's uniformitarianism. This was fun. I agree. I love interacting with you guys. I love the live chat. Thank you so much. I like this better than Zoom. Okay. How would I describe an organism based on the laws of thermodynamics? How would I describe an organism based on the laws of thermodynamics? Okay, so first of all, the laws of thermodynamics, they describe how energy works, right? There's like 4 laws. I taught you 2 of them. Energy can't be created or destroyed. That's number 1. And number 2, every time you use energy, it becomes unavailable to do work. It becomes unavailable, it becomes degraded. And that principle of the second law of thermodynamics is we increase entropy, which means we increase disorder. So now, because life requires energy, we can kind of come up with a way of describing life based on thermodynamics. Life uses energy, but life uses energy to create order. So life is an island of low entropy. My body, every cell in me is completely organized. It is out of equilibrium with its environment. We're not in equilibrium. So life is an island of low entropy. We are ordered, right? We're an island of low entropy. That is important. We are out of equilibrium with our environment. I know it sounds weird. You don't ever want to be in equilibrium with your environment, man. It's bad. You're dead. If I were in equilibrium with my environment, I'd be carbon dioxide, water, and a few salts and minerals on the ground. That's equilibrium. I am out of the equilibrium. Not only I'm about 30 degrees warmer than my office right now, I also maintain all types of chemical balances inside of each of our cells that are all different from what's outside of me. So I hope that works with the thermodynamics. Oops, thanks about the uniformitarianism. Hey, no worries. There's 3 chapters. Sometimes you miss a concept, you miss a word, you miss something. Don't No worries, no worries. That's why we're here today. Okay, can I go into further depth on how carbon is the element of life and how is it essential for organic molecules? Okay, that's a good question. I actually did a video on YouTube called about carbon, but I don't know about you, but some of us are getting death by YouTube videos. Oh wait, are we on YouTube? Sorry guys, but it's a good way to interact with you. Carbon. Carbon is incredibly important for organic molecules. And in fact, of the 92 naturally occurring elements, carbon is basically the only one that is a center of organic molecules. Here's why. One, it has 4 valency electrons. It needs 8. What that means is carbon can form 4 covalent bonds with other molecules. That is important, okay? Not only can it form 4 covalent bonds with other molecules, it can form covalent bonds with itself that are stable, okay? So that means that carbon can form large, complex molecules that are stable. So if you think about carbohydrates and fats and proteins and like vitamins like vitamin C, vitamin A, vitamin B, carotenoids, beta carotene, these molecules are based around the element carbon being able to form 4 covalent bonds and forming covalent bonds with itself to create an incredible variety of molecules. Oh my gosh, there may be millions of organic molecules in the universe, all centered around carbon's versatility of forming stable covalent bonds with itself and with oxygen, nitrogen, and hydrogen. Okay, these questions are saved in the recording, right? They should be. Hey, Garrett, good to see you, man. One of my long-term buddies from Florida State. All right. Anybody else got any more questions here? We talked a little bit about some astronomy here, and I actually do have a couple of those questions on the test. I actually pulled up the test so I could make sure I could answer your questions about it. And like I said, if you guys are scrolling through it, got a question about some of the material, now's a good time. If not, I'm going to sign off here. All right. I've said about everything I need to say here. All right, guys. Well, hey, this was fun. Like I said, I'll be on email until Friday about noonish to answer any questions you got about this material. Remember, open book, open note. Take your time on it, guys. Look through the book, study, review this material, get the answers right. Don't rush through this. There's no reason to rush through this test. I'm serious. Okay. And hey, you're welcome for doing it for the review. I really enjoy doing this. I actually really miss seeing you guys in class. I know the 100 section was an online course, but the 03 section, you guys we were supposed to see each other every Tuesday and Thursday, and I miss you guys too. So you guys are welcome, and we will do this again next week. All right. You guys are welcome. Thank you. All right. Have a good weekend, and like I said, feel free to hit me up with any questions you have between now and tomorrow at noon. Okay. Oh, you got it. Thanks for the further explanations. You got it. Yeah, you guys are more than welcome for that. Even if it's in the book, I'll tell you where it's at if I remember, but don't ever feel bad about asking me something that's in there. That's cool. All right, guys. Have a good weekend.